ahead today? We got the good camera today. Hopefully the audio is working.
Apparently we are live.
All right. Somebody tells me we're live. So today is September 2nd, 2025. Here at CSE466 inside of ASU. The camera still can't track me. We're off to a good start. So I'm going to be short and quick because this is not my day to lecture. I'm just going to talk about some logistical things. And yeah. So state of the class. We had 132 people registered at the beginning of this. Right now, probably a little bit more than half have dropped. I looked at it yesterday, and that number will probably grow a little bit between now and the drop deadline, which is tomorrow. Of those half of people who have not dropped, half of you did not hit the checkpoint. This concerns me. This concerns me a lot. What can we do to help from an instructional side? I'm legitimately asking and looking for answers. Yes.
Well, first checkpoint is kind of an insight on how the rest of the semester going maybe possible to credit.
I'm sorry, could you speak up a little bit?
Maybe just some possible credit if this is how the rest of the semester is possible to go down.
Okay, so for the stream, the proposal was, hey, if this is how the semester is going to go, maybe we need some extra credit. You didn't suggest this. I'm going to paraphrase a little bit because other classes have done this. Maybe we just like curb this and move on, right? Just somehow just deal with it and move forward, right? That's one thing that hypothetically we could do. I'm going to say that that's not the path forward, not because I don't believe in extra credit, not because I don't believe in curbs. I do believe in extra credit. The problem with doing that with this module and this class as a whole is that this content builds upon itself. So unlike CSE466, where you have a module that is on web, and then you can, hey, I didn't get that, and then I'm going to do binary exploitation, and that's unrelated, right? If I didn't understand web, this binary exploitation module doesn't matter. And then I'm going to talk about crypto, which is, again, a separate unrelated topic. This course relies on the exact same skill set and builds upon itself as it goes forward. I understand that from a grade standpoint. Is there anything other than somehow inflating the grade that we can do? Yes.
What do you actually demo? Like the last few times we've done the demos, what are you doing? Is it stuff from pwn.college, like content from there that you're doing?
The question is, what do we demo? So did you watch the stream from Thursday?
I just come to class.
You just come to class. Okay, so that's your first mistake. Because as we said in the syllabus last week, Thursday, or 2 weeks ago, Thursday, each lecture, Tuesday and Thursday, are separate content.
Oh, I come to all both classes.
I'm sorry, you come to both classes.
Yes.
So you did see last week,
Yes.
Thursday. Okay. And what we demoed was the question. I said, hey, class, what do you want us to talk about? What are you stuck? The statement was canaries. I threw together a demo on canaries. We ran through it. I used various tools, talked about what's going on inside of program's memory. The demo challenge that I had was a proxy for problems that you have in the material. Like, it was designed with that intent. You may have not encountered the specific problems that are specific challenges that paraphrase that, that have the same sub problem, but it was designed with that intent.
Okay, well, that's what I was just going to suggest, like demo stuff that is covered, but you already did that.
So I do. The thing that is different is I don't demo the literal challenges that you have.
Yeah.
The reason that is the case is if I do that, ultimately what happens is people just copy the code at the end of the demo and they get a flag and they don't learn anything, which is a problem. Any other suggestions that we could do? Yes, please.
Honestly, that I know was like the Boolean spell binary exploitation was like really easy, and I just felt like it was a kind of a crazy jump between the Boolean spell binary exploitation and the first module binary exploitation that y'all know. That's what I think, because I was able to do all Boolean spells like the binary exploitation in like an hour, but then I thought it was like a kind of a big jump from like the Boolean spell binary exploitation to the y'all know binary exploitation.
Okay. So the statement was that the content in the orange belt binary exploitation was pretty easy, and jumping into this content, it was significantly more challenging, which is an interesting observation, because back in the day, if we go back like a year, they used to directly follow each other in one big module. Good feedback though. Yes.
This might be a bit unreasonable, but very possible. Like I know that the structure is very set up so that ideally by the time you hit the checkpoint, you realistically have done all the easier ones, but you should build up to the harder ones. But maybe have it set up so there's actually like a critical flag that you realistically want to get in order to get the checkpoints, instead of just having to be like percentage of done. Because I know that for me, I was able to dump it a little bit do some easier ones in order to get the checkpoints.
Okay. I'll think about that. And there's one more suggestion. Yes.
This is something that I noticed. Again, I took 265 for this, and so I feel like the Discord activity is a little bit, just me seems to go a little bit less. So potentially having like, maybe just encouraging a little bit more Discord, because I feel like students aren't helping each other as much as before as 265. So maybe like encouraging some peer-to-peer appropriately.
Okay. I appreciate that feedback as well. I do want everyone here to succeed in this course. And so the 50% drop rate is not a big deal. That is part of this course for, I don't know, 5 years, give or take. 50% people don't have the time in their semester to tackle this material, right? And I get that, I understand it. The concerning thing is the first module, not hitting that checkpoint. So this was kind of our rigid plan that I said this is what we're going to do. I don't believe in curves, but I do believe in like trying to meet students halfway. So what I'm going to do, or what we're going to do here, is we're pushing back Rev. That's why it wasn't launched. We're going to launch that on Friday. The idea is this gives you this whole week to work on the program security stuff that you haven't solved. We'll sort out what this means for the rest of the class as far as, okay, this was all rigid to the end of the semester, whether that means I drop a module, whether that means I make some module extra credit when we get there. We may do that. But in order to succeed in the course, we have to go through these fundamentals. So this is what we think is the best way to try and meet you guys halfway. So we're delaying Rev by another week. I'm also going to, as soon as I'm not up here on camera, change the checkpoint. So I'm going to move that to be the due date. So that means those of you that did not hit the checkpoint have the opportunity to get that credit. Hopefully this is just, hey, there's a big gap between the orange belt where we are now. Hey, I got a bunch of cobwebs. I need to, flush this out, put in some time. This gives you the opportunity to start the semester off on the right foot and gives us the opportunity to fill any knowledge gaps that you may have. A couple things that people brought up that I'm aware of. The grades page is a little bit wonky. I think it's showing Rev, and meme extra credit is apparently double dipping.
Yeah.
Okay. So we want to help you. We want you to succeed. We really do. However, with that in mind, if you're still like, hey, this isn't for me, just a friendly reminder, the drop deadline is tomorrow. So if you are contemplating dropping the course, please make the decision that's best for you by tomorrow, because after that, I believe you have to take either a W or whatever grade you end up in the course. As somebody mentioned, I also had this observation. There is not that much activity on the Discord. A big part of what makes this class work is when you are stuck, that you ask a question. Just today, while I've been here on campus, I've had 3 or 4 people ask me the exact same question that they were stuck on, and it was something silly that any one, like 1,000+ people on the Discord could have answered and got people unstuck. And people are telling me that they spent a day, several hours on something that could have been resolved very quickly by just asking for help. So I just want to sanity check. I think everyone has the CSE466 role, right, on Discord. Yeah? If you do, the other thing that I want to sanity check, which Michael is driving here, is that you have visibility to these core material channels on the Discord. The important one being program security, which is open to the public, where you can ask any questions. And there's tons of blue belts. There's tons of TAs that'll answer your question. Like, you will get an answer if you ask a question here in this program security channel. Similarly, if you want to write up, some lengthy story, there's a core material forum. You say, hey, I'm in this challenge. This is what I'm seeing. I don't know. It's not working. What's happening? Question.
So the structure is now different, right? It's all just one big channel that the like posts that you make for each challenge.
Okay. Yes. So the structure of the Discord is there is one channel for program security, which is just one giant chat room. Just throw out whatever you're stuck on there, right? Cool. Hey, I'm on this. That's someone will answer, right? The other way that you can do this is if you like making posts and using forums, is you can go to core material here and new post. Okay. What changed compared to 365 is they used to have this automated bot command. You hit /help and it drops you into some mono thread of insanity where there's 1,000 posts of everyone just saying what they're doing. Ideally, we don't do that. If that's what we end up converging on as a class, that is what it is. But I'm hoping that by creating a post that is more structured around whatever you're stuck on, that post is about helping you, not here's everything to possibly do in this challenge. But I recognize that sometimes it's easier to title something level 12 stuck. Yes.
Going on that, two things. First of all, which one do you want us to do? You'd rather have us just go to that big single channel ask question, or make forum posts?
My personal preference is the giant big channel. However, use what makes sense to you. It's about you getting help, not what I think you should do on the Discord.
And so then the second thing, this is again more proposal I don't expect reacting on. Maybe for it's also set up so that for this course, once it's 6 students, they can set up per challenge well, I guess forms.
No.
Just like go through and pass.
Fundamentally, I say no. If you guys want to make that and you build that yourself, I think that's a horrible idea. But if you do it, you did it, and I'm not going to delete them. Right. I'm not going to help everyone recreate the Library of Alexander at pwn.college. Right. The idea is you talk about concepts, not, oh, I'm on level 12. I click on the level 12 forum. I scroll down and I do what YOLO hacker swagman 20 says to do. Right. I just type these commands. If there isn't a little bit of friction in finding that information and having that discussion, then learning isn't happening. What you're going through is rote repetition of what you see. That's the idea. And now the flip side of that is actually way more work for the instructional staff, because we, generally speaking, need to be available to answer your questions for that to work. So it isn't I want to penalize students. It is, I truly believe as an instructor that is the optimal way of exploring and going through the content. It's more work for us. It is more work for you, but it is really being done in the best interest of learning. I understand the request though.
And just as a quick little side note, if you are in the Discord and can't see these channels for some reason, go up to this little pwn.college dropdown where you can look at everything and click this show all channels button. So if you're for some reason not seeing like the 466 on topic and off topic or any of these core material forums, make sure that you're actually seeing all the channels. If you can't see them, you can't get help.
Can you flip to something where there's home tools? So the question that I got hit with like 4 times is, hey, I saw Robert's cool demo last week, Thursday, right? And he was in a terminal, and he's over here, and he goes, from pwn import star, P equals GDB debug something.
You might want to do that in the dojo. This is going to work on my local system.
This is why
There we go.
Okay. And so I'm trying to do something like this. You trolled me with this demo.
I did. My bad. Yes, I do want to exit here. IPython 3.
Cool. Go. So I'm in a terminal. I do from pwn import star, and then I try and do this. And pwn tools explodes, and I get this error. Right? Could not find a terminal binary to use, set context not terminal to your term. How many people encountered this? Okay. There's a few, and these aren't the people that met me and asked a question today. So that means that there's at least 10 of you and probably half of you like didn't raise your hand or aren't here today, right? This is a stupid thing to be stuck on. Not because it's not a problem. It is, but this is something that you could ask in the Discord. It is not about the core content. You're not asking for a solution. You're just saying, I don't know what this is asking me to do. Collectively, as a class, we probably wasted 40 plus hours on this error message. All right. This is what the Discord is for. All right. You run into something like this, you ask on the Discord, we'll tell you, oh, that's because Home Tools doesn't know how to make a new terminal window. Okay? That's what it is. I'm not saying that you can immediately get that from parsing this, but that is what the error is saying. Home Tools doesn't know how to make a new terminal window to run GDB. There's two ways you can deal with that. If you are in the desktop environment like this, then you need to run this command. /run or context.terminal equals run dojo bin xfce terminal -e. We do that. Now when I run GDB, it now knows how to pop up a GDB window. And we have a similar setup to what I did on Thursday. All right. The second way that you can make this work and just avoid this error is what I did. I don't expect you to do what I did. It is my personal workflow. I do everything inside of tmux. If you took 365, I believe last semester, I could be wrong here. They had a little module back at the beginning in the Linux Luminarium. They would say, hey, this is tmux. tmux is a terminal multiplexer. What that means is that while I am inside this terminal, tmux allows me to spawn more than one terminal. Pwn Tools is aware that it's inside of tmux. So if I just from pwn import star, GDB debug, because I'm in tmux, it will do this split in-house. All right. But now you have to worry about how do I select windows inside of this thing. There's going to be a bunch of terminal shortcuts that you may or may not know. You do have to learn tmux. I don't think it's that crazy. Use what makes sense to you. If you don't want to learn a new tool, do it in the desktop with that magic xfce command that I just showed. Right? These are the type of things that can be resolved in 5 minutes by asking a question instead of suffering in silence, and why we have this Discord. Can you get me back to my slides? I'm running late and I'm sorry.
Oh, you're good. Don't worry.
Cool. Office hours. We said we're going to hold them. This is what it's going to be. I polled some people. They said Saturday afternoon is probably the optimal time because there are people working on the weekends. So I'm going to do Saturday on Discord. So in a Discord chat, I will work on your challenges. I'll look at your code. You can share your screen. You can do all of those type of things that you would expect. Saturday from 2 to 3. If there's a lot of questions, I will run for 2 hours until 4. Michael will do the same thing. He, however, is a morning person, unlike me. So he will do it Friday, 10 to 11, running for an extra hour if needed. Office hours are not recorded. So it's show up and get help or talk. Office hours will work on your actual challenges. We will work on the demo, the things that you are working on, not the actual demo chals, right? This is to get you unstuck on literally what you have. We will look at your code. We will talk about it. Should be useful. Is that a hand? I'm sorry?
Office hours on the syllabus are still not.
Yep. So those are all of our TAs and other core staff that are working with us. This is just for us too.
These are additional office hours.
Yeah.
So Monday, Wednesday, Friday from 4:30 to 5:30 over in the mezzanine. That is when we have 3 different TAs that can help you, and they will in person sit down, work with you, try and get you unstuck. In addition to that, there is Tiffany's office hours, which I believe are remote Tuesday morning. Again, can give you hands-on help. And then there are going to be Michael's and my office hours over the Discord. Again, remotely, hands-on, look at your code, help. Right? We want you to succeed, but people have to show up and let us know what you're stuck on. If you suffer in silence, there's not much we can do from an instructional standpoint. Yeah, I already said that. Boom, I'm done. I'm not giving a demo of my codes.
All right. The demo, a lot of you guys talked about that GOT was challenging. And so we're going to demo just a couple little things about the GOT. I'm going to run through a demo of basically like how we can leverage leaks in order to get to all of these various places that we need to go. And then mostly just like looking at what the glue process looks like. Like, why are we using this tool? Why are we using this tool for that? Like, how are we interacting? Like GDB, IDA, Python, program. There's a lot of moving pieces around here. And so just like the process of solving challenges starts to become long when you have to juggle these tools in like really inefficient ways. So we're going to look at workflow optimizations. And essentially just taking a look at how we can do something like leveraging like a stack leak in order to figure out like where things are in memory. Essentially just what does that solving process look like? Let's see if I can turn this to look at me again. It's not working. All right. So basically I've written a challenge. You can't see the source code because I've hid it off my screen. And what we're going to do is build it. And I'm building two different versions. So basically I'm building a version with -s, which is going to strip the binary. And then I'm just building a normal version. And our goal is to exploit them. We have a blank exploit script. And so the thing that I really want to hone in on here is like, how do we approach like the reconnaissance process of like, it's kind of like what I call it in my head of just like figuring out like, what are we doing? Like what our foundation is, because it doesn't make sense just to start writing exploit scripts and trying to go too quickly. So common things that like you're always going to do at like the start of challenges is like running checksec on things. So for example, I told you how these are built. We see that they have no rel-row involved. Does anyone know what rel-row means?
It makes the GOT table not writable.
Yes. So basically, rel-row stands for read-only relocations. And essentially, when we have this enabled, our GOT is no longer writable. And instead, it's basically set up at load time. So therefore, when we're actually executing our program, we can't write to it. But here we have no rel-row, so it's free. So we can write to it. Now, other things that I like to do when I'm just like looking at files is just poke around them a little bit. Like you can learn a lot just by interacting with things. So for example, there I didn't really learn a lot, but some other things that we can do, for example, is like ltrace. We can see right away that I'm hitting a read. Ltrace is going to look for like library calls. So we can see that, okay, we have like a read call. I'm getting what looks to be some weird data coming out. I'm seeing a puts call, another read call. Like these are very, very simple things that we can do. I'm seeing a string like hello hackers drop out. Like I'm learning things about my binary like very rapidly. Similarly, like I can strace this to take a look at what's going on. So maybe I need like a more detailed view of all the system calls. So taking a look, we see some hellos, we see some writes, and there's a lot of places we can go. For me, like my preferred place to start is just to look at things in IDA, since that's what I'm the most familiar with. Where is my IDA window? It is no longer existing. Let's get IDA up and running. Where did I just send that? Boom. All right. So yeah, it's big enough, I hope. And so when you got, oh, interesting. Hold on, technical difficulties. I'm going to unplug that and it's going to break OBS. Let's see. All right, that's still going. Hold on. Might it always be? All right, hopefully that's working now. Oh. Okay. For the stream viewers, what's happening is my projector is flickering on and off. Why? Split view, just try.
We make it not full screen. That's what might be the reason why I can start doing this.
I think it's trying to juggle. I think it's trying to juggle things, yeah. All right.
You need like window that you can be quiet.
Yeah. I don't know why it's trying to go full screen. That normally doesn't happen. But I think if we cheat and do that, it's like ghetto full screen. Okay. Interesting technical difficulties. Let me make sure this stream is still hopefully working. Someone in the chat will tell me otherwise. All right, so let's actually open the right file. That opened a second IDA window. All right, so when I open a binary up in IDA, the first thing I'm doing is literally just trying to figure out like what is the base case of what's happening. And so let's see, can I zoom you in at all? No. Font 16, there we go. And so, for example, right here in main right away, we're only calling one function. So I'm just instantly writing this off, like just going, okay, what is vuln now? When we double click on that, we go into a function that actually looks like it's doing something now. And so the first question that I'm always asking myself is just like, how is my user input being taken into this program? I ran the program a couple times earlier with ltrace and I noticed some read calls. And so to me, like whenever we're doing like these pwning CTF challenges, your input is almost always going to be relevant, and figuring out how to validly input into your program or invalidly input into your program is generally always my first step. Like, what is my input? What's happening? And what does it affect? And so the way that I'm always doing that is I'm just looking for where my input is being dragged into the program, whatever function that we're using. It could be like read, it could be scanf. Let's see, there's a lot. It could be gets if you're crazy. And essentially just looking, okay, where's my input ending up? Where's it being used? And so right away, IDA is telling us, hey, we've got this buffer, and the only place it's being used is in a print call. So right here. And so, of course, hopefully some of you are already looking at this and seeing what the problem is, which is that we have this char buff that IDA has identified as basically being 64 bytes long. And then we are trying to read a very large amount of data into it, hex 100, which if we want to look at that, remember in decimal, we can right click it and change our data types in IDA. So we're reading 256 bytes into a 64 byte buffer. Problem. Hopefully this is something we can take advantage of. And so let's get rid of you now. So now let's begin to actually dive into what that looks like. So not challenge. So I know that my function that I'm targeting is called vuln. I also know that I want to be looking at what my input is doing to the stack. So when I know that I have a buffer overflow in theory that I can exploit here. I don't know exactly what the results of the buffer overflow are going to look like yet, but I've identified that a buffer overflow does exist. Like there's clearly a size mismatch here. Now, these are the kind of things where in these early challenges, like the bug is supposed to be obvious and supposed to just kind of fall out and be, okay, here's where the memory corruption happens. And so now I want to look at what the observable effects of this memory corruption are. So to me, that's always just breaking in GDB basically right before my input goes in, sending in my input, and then looking directly after my input goes in, and then just kind of measuring the difference and just kind of looking at it. So the easiest way for me to do this is just to break on read. So we can run our program. I already put a breakpoint on vuln, but I guess we don't really care about that. And then I get to my read function. Now, because I'm inside of the read function, note that whenever you put a breakpoint on a function just like that, it's going to break you on the first instruction inside that function. I personally like to put my breakpoints right outside, right where the call site is. So I'll show you what I mean by that. So if I disassemble my vulnerable function, then just kind of start scrolling through here until I see a read call. So right here, this is where I want to break. I basically want to go, okay, right before read, right after read. So those are two places I'm interested in. So let's look at my breakpoints. Let's delete these two. And then I'm going to set a breakpoint right there. So that's vuln plus the offset of 62, which is this guy right here. And so when we do it like this, note that we're setting like a relative breakpoint. So every time we run this code and then vuln potentially moves around in memory, we're referencing the symbol vuln plus 62, so it'll work fine. So we're going to set our breakpoint, run our program. And so now we can kind of start to get an idea of what's happening, because remember, like, it's a read call. We know what the arguments to a read call are at this point. And if we didn't know, we could look at the man page. So in this case, we hopefully should know by now as a class that the second argument to read is that buffer of where your data is going to be ending up. And so I want to know, okay, well, what's there before I read? So I'm going to use my tele command, which is basically just going to telescope through the stack and kind of take a look at what's going on. Maybe I hit this a couple times, and I just want to save this off. And so I'm the kind of person where I'm just going to take it and I'm going to dump it into a file and think about it later. Basically just snapshotting that state in a way that I can come back and concretely look at. Then I want to send some input into the program. So I'll continue. And let's remember that we broke at that read call. So when we continue, it's just waiting for our input. So I'll send in a couple of A's. Note that I probably want to finish from this function instead of continuing, because I want to break right after it returns. That's what finish is going to do for us. So basically, I have sent those A's in. I finished from this read call. And so now we're right on the instruction after that read call. And what we can do is run those same telescoping commands and kind of look at the difference here of what's happened. So there's fancy ways to diff this with like a text editor that I do sometimes if the stacks get really long. But in this case, I'm mostly interested right up here at the top. And we know that here's our input. So we can see our hex A's start to show up here. And I know that anything that's within a hex 100 bytes, so essentially anything in this dump, is something that I could potentially put an A on top of because I have the ability to do that with this read call. And so now the question becomes, okay, well, what can I do? What are my options? Like, this is the part where you as a hacker have to start reasoning about what you're seeing. And so if we go back to IDA, we're going to notice that we have a very fun print call right here on line 12, which it's printing our buffer, and then it's printing %s. Now, remember that strings in C are null terminated. So whenever we see %s like this, like, how does this actually work under the hood? And if you go and look at how this actually works under the hood, it's essentially just outputting byte after byte after byte forever until it sees a null byte. So we can weaponize this by using it to potentially leak things out of memory. Meaning, let's say right now, for example, that maybe there's this pointer that's literally 8 bytes under where my input started. Remember, this is because our stack frames, they get allocated, they get deallocated. We don't properly clean up the data. So it's very possible that you just have like leftover pointers unless you are explicitly zeroing out things. Just to note that home, we'll note that at no point am I zeroing out the contents of buffer in this vuln function. Like, you're not seeing like a memset 0 or some weird decompilation that's setting it to 0. So it's just uninitialized. This means potentially there could be things in that buffer that are useful for us to look at. So let's say that maybe I wanted to leak out this very, very next address that just happens to be 8 bytes below the start of my input buffer. Now, what does this get us? Like, what is this memory address? Like, it's an address on the stack, so I'm assuming it's relevant somehow to something somewhere. Like, our program put it there for a reason, but we want to know what it is. So if I come over and run my vmmap command and feed it that address, we can see that this 7ff address right here is actually a part of libc. So if we were to leak that out, we're getting a libc address. And then remember that because these binaries are objects in memory, they have a base address, and then everything's just kind of offset statically. Once we get one address out of something and we know where it is in the binary, we can very easily calculate everything else. And I'm going to demonstrate that. So, for example, so like one thing that I'll commonly do is I'll just run down here and go, okay, well, if that's in libc, maybe this address is in somewhere else. And then I will just literally just run vmmap on things and be like, okay, what is this? So for example, these with 7ffff all kind of look like they're coming from libc. This 555 looks different to me, so I want to know what that's coming from. Okay, that's coming from inside our binary, so that's something to note. So like if we leaked out this hello hackers string address here, we would have an address in our binary, which we could then resolve to figure out where things in our binary are as well. So let's reinforce that really quick. So one thing to note is, so in IDA, what I'm going to do to show this is I'm going to go to View, open subviews, and segments, your binary has a lot of segments in it that do different things. So one that we've been talking about a lot recently is the global offset table at the GOT, but as you can see, you've got a lot here. The thing to remember, though, is that these are all contiguous, like in memory, when this binary gets loaded into memory. So when I go look at things with VMMap, let's make that bigger, we're going to notice that our binary is being loaded in at this offset. So I'm just looking through it and I'm picking the smallest one. So I'm grabbing we call this a base address. So this would be the base address of the leak me binary. And what I can do in IDA, and this is more useful when you have binaries that like to move around a lot, or you're dealing with like a strict binary, is I can rebase IDA. Basically meaning, where is it? Boom. So if I go to edit, segments, and then rebase program, you'll want to remember this. This one's very helpful. I can put an address of the image base or the binary base here, and then I hit OK. And then IDA will go through and automatically recalculate everything. So, for example, now I'm getting those nice memory addresses that I got in GDB. Question.
A question from Twitch. Can you talk about a way to quickly search things in memory? Like, say you wanted to find the GOT.
Okay.
The best way to do that than just scroll through thousands of memory locations in GEM.
So the question is how do we find the GOT without doing something like this? How do we find the GOT without doing this? Well, that's one nice way, is the literal command GOT. I would recommend that one. So this is a GEF feature. Basically typing in GOT when you have GEF will tell you exactly where all the GOT entries are located, so you don't have to guess about it. One other thing we can do is that if you bring your binary into IDA and look at this segments window again, so remember I went to view, open subviews, and segments. Also, just if you're bored, go click through these. They're all cool. They're all useful. And we can find our GOT entry. And then if my binary wasn't, if I had not rebased my binary, we would see a fixed offset here. So let's see if can I undo that easily. Let's go with, let's see, we'll rebase back to 0. And we can see that this global offset table is at the offset 3488. Or maybe we're interested in like a specific one. So maybe I want to look at this puts pointer at 34BO. And so I run VMMap, I get the base address of my binary, and then I add that offset of 34BO to it. So XGX plus OX34BO. And then there's our GOT entry for puts. Does anyone have any questions on that process? All right, cool. So let's see, where was I? So we were talking about looking at the stack and trying to leak things. And we've discovered that with my snapshot of memory dumps here, I can leak addresses that we found out to be in libc. I can also leak something that is in the binary. And if I continue to explore these other things, I might be able to leak them as well. But let's take a look at this one string that's in the binary, because guess what? If I leak out this pointer to hello hackers, because it is pointing into the region of my binary, like in memory. So like, once again, just to reiterate, like if I take this address and then we run VMMap on it, we're going to see that it literally is living in the loaded binary. And so if I leak this address out, I can calculate the base address of the binary. And then from the base address of the binary, I can calculate exactly where those GOT entries are. So let's take a look at how that might work. So now we're going to start exploiting a little bit. And remember, my goal, my thought process so far was I found a buffer overflow, and I found that the contents of my buffer overflow are leaked back to me. And so therefore, I have the power to leak data off the stack. So let's take a look at weaponizing something like that. So I'm just going to make a process. Let's make that bigger. And then one question that I guess I haven't answered yet is how far is my input buffer to this pointer that I want to leak? Now, there is an argument to use cyclic values because I'm literally staring at the memory dump. I think personally, I would rather just do some math here. So one thing that I'm always doing when I'm working on challenges like this is I almost always have like a Python window up just to do math. And it's because what I can do is I can come in here and go, okay, well, let's see. I just deleted that. There we go. So I can come in and take this memory address of where this string is, and then I look at the location. So I grab the literal location of where this pointer lives in memory. So that's this DE8 address. And let's copy that out. And now I want to take the start of my input buffer, which we know is this DE6 value. Remember that I observe these both on the same run. Like if you get one from one run and one from another run, it's very possible that these could move around. So make sure you're getting them all from the same execution of the program. And then we'll just do some math. It's negative 72, but it's the same way. So basically, I know that there's 72 bytes between the start of my input buffer and then where this pointer lives in memory. And that's always going to be consistent. That distance of 72, no matter how many times I run my binary, these values on the stack are not magically going to reorder themselves unless I rebuild and make a new binary that does something else. Anyone have any questions on this part so far? Because
What's the reason behind you setting this base address all at fives?
setting. So are you asking like why the base address is just fives?
Well, yeah, you set it that way in GDB and then.
So I didn't set that. The computer set that. So like when I ran GDB and with the binary, all I did was start the program, and then GDB assigned a base address to my binary by loading it into memory. So that was handed to me. The reason that I want to note it is because once I know where the binary lives in memory, I can start to calculate things.
No, I understand that. I'm pretty sure if you check your GDB in it right now, it'll be like set base to that the whole vibes in it. Right. I'm pretty sure this is not like what GDB would do on its own.
That'd be really funny. My GDB init is literally just loading gap. So that might be a get feature.
Okay.
But there is no rhyme or reason why your binary base address could be anything.
Okay.
Like as long as you can know where the base address is, like if you leak it out or observe it in any way, everything's just an offset from that. So my base address could literally be like 1337000.
It's like everything you run is going that same number. So
Oh,
it's setting somewhere.
so that's GDB disabling the randomization, and then that's just kind of how it ends up.
Okay.
I don't have like a good answer for why it's 55555 and not 66666, but it's designed to be consistent so that you can observe it.
Sure.
Okay. All right. So just to quickly get us back, I calculated that there's 72 bytes between the start of this buffer and then where this pointer that I want to link is. And so the theory is that if I fill up all of this distance with A's, and then we go to print it with that printf, we're just going to start reading out data until we encounter a null byte. And if I fill all of this up with A's up until the end of this pointer, the last couple bytes that we're going to get out of this printf call is going to be the literal pointer value on the stack there. And then we can grab it, and then we can use it for math. So, got my process. I know that my distance to the pointer was 72 bytes. And I'm just putting that in a variable so I don't have to remember it constantly. And then I just want to start simple. So we're going to send in 72 A's and then see what happens. And one thing that I like to do when working on this is I like to set my log level to be debug. And you will see what this does very shortly. So Python 3 leak. Basically, this debug mode allows you to specifically see the literal bytes that are being sent to and from your program. It's very, very useful if you're having issues like off by one, or I'm not sure, like maybe I'm not processing my output correctly. And what we can see here is we sent in 48 bytes of A's, and then we got back 4 E bytes from our program. And we can see that we got some A's. This little star is PwnTools telling us that this is just repeated content. So more A's. But then we can see at the very, very last one, we're seeing 6 bytes of a memory address leak out. Any questions on this so far? Okay. So now let's actually get it out. And I have this wonderful strategy for getting these things out of the program, which is instead of using all A's, I will put like a single B at the end. And then all of a sudden, my output has a very recognizable pattern. And I can do receive until I get like a bunch of A's with a B at the end. Because I know that like basically my input is going to be reflected back to me because of that printf call. And so I want to know exactly where my input ends and the data in the program starts, and I don't want to worry about doing math. So I just slap a B at the end of the input and I look for the end. And at this point, I'll run this just to demonstrate. Oh, I should do a p.receive as well. At this point, what we'll notice is, or I guess Puntles doesn't show it that well, but essentially, we're going to read all the way up to this AAB. And then if I print out what I'm getting raw from this, oh, come on. Oh, I got to save my file. That's funny. We can see that those last 6 bytes I'm getting because I read everything up until the AAB, and then I'm going to receive the rest of it, which is just going to be those last 6 bytes that are a memory address. It just prints out the representation. So instead of seeing like random string characters, you're getting this. It's just to show you. Nothing you need to know. So then the way that I like to get my leaks is this wonderful construct that you'll just learn eventually, which is I will explain exactly what this does. And then we'll print that out. So here's our leaked address, and then here's how we're getting it. So I know that I'm getting my input back to me. So I'm reading up all the way until the very end of what I've just inputted. And then I know that the next 6 bytes that I receive, which is this p.receive 6, are going to be those leaked memory address bytes, because that address is spanning 6 bytes with 2 at the end that are just like nulls. And so I'm adding in those 2 null bytes, and then I'm using U64 to unpack this 64-bit number into a leak. And now I print it out, and I get this memory address. And remember, this memory address is going to change every single time I run the program, like 59A, 638, 59A again. This is why getting leaks is important, because you don't have to start dealing with all this randomness. Like if I had to guess this blind, it's functionally impossible. And so now, let's say that I want to use this leak to do something. And so I have to turn this leak into something usable. And so the question becomes, okay, well, what the heck did I just leak out? So I'm going to drop a p.interactive at the bottom, which basically just means, hey, hook my process up to the actual program underlying it so that my script doesn't exit immediately. Because if your script exits, it's going to kill your process and you can't debug it. It's annoying. And then we're going to dive into the wonderful world of GDB. All right, let's quickly do it like that. All right. And so all I want to do is just figure out what is my leak. Like I leaked a pointer off the stack. I want to examine and figure out what this value is actually doing now. And so we are going to continue. Why am I not getting something back? Where's my leak? Come on. All right, well, there's some GDB insanity happening, but why? Oh, I know what happened. Haha, that's funny. I forgot to print out my leak. When you forget to print things, they don't show up on your screen. Thank you. That needs to be gdb.bigdebug again. There we go. Now, when we continue, we should get our leak. There we go. So now we have this memory address, and the question is, what the heck is it? So all I want to do is just tell you and take a look. And it turns out this is pointing to some string, and if we want to know where it is, we know it's in our binary. But let's actually figure out like what our binary base address is now. And the cool thing is because we're looking at a concrete execution of the program, like this is really happening. Like, so if I just go to vmmap and then I grab the base address of my binary, let me pull this out a little bit. And so I go, okay, well, here's my current base address. So observed base adder, we'll just dump it there. And then we have like an observed leak. So that's this value right here that we leaked out of the program. All I have to do is do this math once. I get a difference between them, and that distance between the base address of the binary and the observed leak, because it's in that binary, is always going to be consistent no matter how many times I run this program. And so we can take this leak, we subtract from our base address, and then we'll get a value. I'll do this in Python just to save some time. I closed the wrong terminal. So IPython 3. Then we will do some math. And we find out that the difference between this is 8,460, which, taking a look at that, is hex 210C. So in theory, we take this value, and then we subtract 210C from it. Oh, I should hex that. And this is our binary base address. So every time we observe this leak, we can perform this calculation on it. So this guy right here, leak, and get our base address. So binary base address. And then we can print that out. All right. Oh, let's do that again. Settings. And so now I get my leak, but most importantly, I get my binary base address. And if I come check my VM map, our base addresses now line up. And all I had to do was some math. So just some observing and some math. Any questions on that part so far?
Just show the code.
Yeah. So just to run through really quick, we know that there's 72 bytes between the start of our input buffer and this pointer we want to leak. We know that the reason this leak is possible, just to remind you of why this is possible, is because our input is being handed back to us with this %s, meaning that we print every byte from the start of buffer until we hit a null byte. So if we just run a whole bunch of A's up against important data, it goes all the way through our A's and then goes, okay, well, there's no null terminator, so this must be part of your string. And then it goes data, 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 until it hits that null byte. And we are leveraging that because we know that the 6 bytes after this 72 distance, after we put in 72 A's, is going to be a pointer that's in our binary. And then we can use that to get the binary base address. Okay, so now, a question?
How do we know that the leak is to Tennessee from the software?
Got it. It's because I observed it. So if I GDB, and then let's go right before that read. So let's take a look at that bone call again. So we're going to read, so bone plus 62. And then we're going to run that. Basically, what we know is that we leaked this value on the stack. And so we know that by running VM map on this, that this value lives in my binary. Note that it doesn't live on the stack. It's not like in the heap somewhere. Like this is a literal string that's in our binary. And we can confirm that, for example, views, open subviews, strings. We can find this literal hello hackers string in our binary. And because we know where this string lives, so for example, this is 210C here too. And all I did was I said, okay, well, we know this, like we're leaking this out every single time. And the distance from this to this is going to be the same because hello hackers is a literal piece of data embedded in the program. And without rebuilding my binary, the bytes in the program aren't just going to magically start moving around willy-nilly. And so because we observed it once, it's always going to be the same. Does that make sense?
Yeah.
Got it. Okay. So now let's actually turn this into something cool. Because let's say that I want to like maybe overwrite something with this. Now, we haven't found a way to overwrite anything yet, but we'll forget that part for now. Let's say that I wanted to overwrite maybe a GOT entry. So one thing that we noticed at the very start of this challenge was, let's see, I ran checkseg, and we don't have row, which means that our GOT is fully writable. We can even double, triple confirm that by going into GDB. Let's just start the process. I run GOT. The GOT command, remember, it tells us where those GOT entries are. And then let's say maybe I want to overwrite read. And so I can run VM map on this and see this permission value says read write. So it is writable. That's how we can kind of double confirm that. So the question now becomes, okay, well, where are these? So if I go back to IDA, and then let's go back to our segment view, and let's head over to our GOT. So I can do it like this. Like I can go, okay, well, puts is at this offset. And so I know if I take my binary base address and then add this offset to it, then I get exactly where that entry is every single time. But sometimes we don't want to use IDA, and we can actually just use pwn.tools for this. So one awesome feature that pwn.tools has is basically this elf object. And so essentially, if I take this elf object and pass it the path of my binary, and let's actually explore this in IPython first. So basically, whenever I load an elf object, I can query a lot of things about these elf files. Note that, so like if I do dir on something in Python, it'll give me all the built-in functions. There's a lot of things that we can do with an elf object. Another thing, like if you're bored, looking through these is very fun. But one of them is GOT. And so if I take this elf object and then just look at the GOT, it tells us the exact offsets of where all the GOT entries are in the file. So like I was looking at the one for read. So it's telling us that this is at offset 34EO. And if I similarly go over to IDA and look for the offset 34EO, dang, it's the exact GOT entry for read. So that's one shortcut that you can use that I would highly recommend. So once again, we make an elf, we use the GOT entries. And so I wanted to do elf.got read, boom, there's my address, or there's my offset. Now, the nice thing too is because, so let's going back to my script, I make this elf object. So then, oh, I should put two S's there. Let's say that I know the binary base address. I can come in and tell this elf object, hey, here's where you live. And now I can very quickly grab various pieces of information. So let's say I wanted to look at the elf GOT entry for read. Just fancy Python formatting string nonsense. But now, and I'm going to change this to just a process again. Oh, not that. Now, we can see that we've leaked out the address of our GOT entry. And I probably should have done that in GDB so I could show you. So continue here. And so here's our calculated address of the GOT entry. And so just to be clear on how that's working, we've defined this elf object in pwn.tools. Then we've told the elf object, hey, here is your base address. And then because the elf object knows all the offsets, like it's just baked into it, we can do it can do the math for us. So I get my read GOT entry in, and then I can go confirm in GDB, okay, that's actually where the read GOT entry is. And so this is really, really, really useful when you're trying to like just exploit faster. Like there's less reasoning to do with offsets. You leak a binary base address, you dump it into elf.address, and suddenly I know where everything is. And so there's a lot of useful things that we can do with this. So for example, one thing that we noticed was that, let's see, where is it? One thing that we noticed is that we've been leaking this pointer to hello hackers the entire time. We can even use the elf object to look for hello hackers. So instead of trying to say, okay, well, because like we had defined this 210C value on ourselves, manually by ourselves. Let's say that we knew that it was pointing to a string. So I can come in here and go elf.search, and then I'll give it a string. So hello hackers. And I'll show you in IPython what this does first. So basically, when we make our elf file and then search, it's going to return a generator, which is basically you wrap it next and you get the first result. And this will give us the offset to that string in the binary, which is that magic 210C value. And so a wonderful shortcut is instead of reversing to figure out, oh, that like the key intuition here is that you know that your leak is pointing to this string. That's why this works, because we've done the reversing. We know, hey, this pointer we're leaking, it's a pointer to a string in the binary. And so instead of trying to figure out where it is manually, we can just make pwn.tools do it. Anyone have any questions on that? Cool. All right. And so this is awesome because now I don't really have to worry about a lot of the math. Like the only math that we really did here was this distance to the pointer, which at this point, finding that should be approaching riding a bike for you. Like you'll see it a lot. And so we get our leak, we get our base address. I'm always the kind of person where like when I'm doing something like this, I'm going to go confirm it. It doesn't take a lot of time to confirm these things. Like VM map, that's that address. Yup, that looks like the base address of my binary to me. Similarly, like, is my GOT entry correct? Like XGX, boom. Yup, that's my re-GOT entry. Okay, so now we've got all the pieces that we kind of need, but we still don't really know how to exploit this program because we haven't actually gotten that far. And we're running short on time, but we will exploit. So let's take a look at this. So in my function, what I've got going on, and in the interest of time, we're just going to start I'm going to tell you a little bit of what's going on here, is I have this buffer. I have an int that's called v2 that seems to do something cool. And then I have this v3 pointer, which it turns out that this v3 pointer is the hello hackers pointer that we've been leaking out this entire time. Let's go back. So hello hackers pointer. And then what we drop with this v2 going on. So basically we read, we print it back to you, and then we say, hey, if v2 is less than or equal to 0, we're going to do this operation. Otherwise, we're going to recursively call vol. And this is nice because you might have noticed that we have a stack canary. So if we overflow too far and just try to overwrite our return address, we're going to hit a stack canary and smash. Hopefully we've seen that by now. And so the goal here would be to figure out, okay, well, what does use it do? Okay, well, I click on use it, and use it appears to be a very, very funny function. It turns out we can just arbitrarily write 8 bytes to wherever argument 1 points to. And so this should instantly trigger like warning signals in your brain, like do not pass go, do not collect $200 kind of thing. Like we have a pointer on the stack that's just being arbitrarily written to 8 bytes. Now, this is a very contrived example. I will give you that. Like I'm literally just putting a read call in here. But say that this is some function that does some other complex purpose. For example, FizzBuzz uses a similar system like this, where one of the FizzBuzz functions does something to allow you to eventually arbitrarily write to pointers. And so in this case, we can just write 8 bytes directly to it. This means if we can control this hello hackers pointer, we can write 8 bytes anywhere. And so what does this mean? Like, what do we do? How do we exploit this? If I can write 8 bytes anywhere in memory, and I know where my binary base address is already, what do we overwrite? Sorry? Exactly. We can overwrite a GOT entry. So note that we know that we can overwrite a GOT entry because we ran checksec on the binary at the very start of this and saw that rel was disabled. And so, come on, quit. There we go. And so what we need to do is essentially figure out like how to get here. And so if v2 is less than or equal to 0, we are going to go here. And so because I'm currently just sending in a whole bunch of A's, that check is obviously likely failing. One thing that I probably would do is do some basic GDBing to confirm this. Let's run our Python script again. Let's split that slightly better. Wow. Thank you, fat fingers. All right, there we go. All right, so we're going to get our leaks. And then what I wanted to do was take a look at why does this recursive process happen? And so if we disassemble vuln, or we could go look at IDA, basically I'm interested in what's happening at this comparison. So if I hit tab and IDA, it's going to jump us over to our disassembly view. I can see that we have this printf call, which is the line directly above this. And then below it, we move a value from the stack to EAX. We run test on it, and then we jump. So here's our comparison right here. And so I'm interested in what happens in EAX after we move this value in, because obviously we need this to be 0 in order to trigger this condition. So I'm going to come find that, which is, I believe, right here. So at vuln plus 97 is where I'm going to put that breakpoint. And I'm going to have to rerun my program to do this really quick, just because I continued it too far already. But break star vuln plus 97. Then we'll continue. And let's see, can I pull this up? And so we can see that at this point, the value of RAX is 4 A's. There are no working outlets in this classroom. Good luck.
Oh, are you serious?
Yeah. I got a battery you can plug into with 30% charge.
It's all.
Anyway, so our goal is now to make this 0. And so I just want to know, okay, well, where is this coming from? And so if I break right immediately before this, so I would rerun again. So boom, disassemble vuln. That. And then, so instead of this test EAX, I want to figure out where it's loading the value in memory from, just so I can concretely observe it. Just because we've already built up a good understanding of what the memory on the stack looks like. So if we know where it's being observed, we can very easily figure out what's going on. So star vuln, and then we're going to break right at this plus 70, or no, that's the wrong spot. Where is it? Right here. Because we're moving into EAX, and then we're testing it. So I'm going to break at this 94 line right here. So let's continue. And we can see, all I want to do is just observe what is RVP minus 20. So print RVP minus 20. Here's our value. So this would be the literal address where those 4 bytes, remember, we know it's 4 bytes because of dword, are being loaded into EAX. And so for me, I'm just going to tally out my stack and find the start of my A's. And then I'm also going to see, okay, that's there. So it looks like we need to go a little further. So our A's are starting right here at this BEB30. Remember, if I, for some reason, couldn't find where my A's started, I could break on the read call, find out where the literal A's are showing up in the program by looking there. But because we know that they're just ending up on the stack in a location, I'm just eyeballing it. And then similarly, we know that this BE70 address, so this guy right here, is where those 4 bytes are being loaded in for that recursive check. And so we map the difference between them. So here's one address that I observed. Here's that start of all the A's. I'll zoom in there. Our difference is 64. And so now, I want to resize. And so just to kind of show you what's going on here, the goal is and know that these values are outdated because I observed them on different runs of the program. So these addresses are going to be slightly different. The important thing is the relative nature. So I know that 64 bytes below the start of my input buffer is where that value lives, which is going to end up around right here. And so my goal is to keep that row full of zeros. And we can do this pretty easily. So instead of AB, well, so we want to trigger the recursive call the first time, so I'm going to leave it like that. But then on our second call, we will send in just 64 A's. Then I want to send in 8 bytes of null. So for me, that's just P64 that'll just pack it to 8 null bytes, expand it out. Nice. And then I want to put something on that pointer that we know is being used, which let's overwrite a GOT entry. So the GOT entry that I'm going to target is the one that I have contrived for this example, which is put char. Because if you hit X to pull up the XREFs, you can see that this is literally the only place put char is used. So you're not going to run into those funny meme situations where challenge calls puts, win calls puts, but then you overwrote puts. And so it's going to start recursively calling win, and then you run out of stack space, like funny stuff going on. And so because we set up our ELF binary or our ELF object correctly, we set the base address, we can just simply use this guy right here. And we are looking for put char, and then we just have to pack it. So P64. And if the assumptions that we've made about the program are correct, we're going to do one call of this and hit vuln. That first call is going to leak out the hello hackers pointer, and that's going to enable us to calculate the base address of the binary. And then from there, we know, okay, that's where the GOT entry is. And then our second recursive call, we just have to pass this check, get into this function, use it to basically overwrite that pointer, because remember, use it is essentially our arbitrary write gadget that you've presumably exploited and found. And then we're going to overwrite the GOT entry for put char, enabling us to go wherever we want. Anyone unclear on how that process works?
With our current code, aren't we literally just overwriting put char with put char?
Yes.
Okay.
Well, right. So right now we aren't actually writing anything there. We're writing the address on the stack. And then that stack address is passed to this like do it function. And so that,
And that's gonna.
yeah, so like use it. So we're overwriting this literal value that's passed into use it, which is then just directly 8 bytes are written to it. So it's one layer of indirection for that. So let's take a look. And so basically, I just want to observe to make sure that this address is being properly overwritten. So quit out of that, quit out of that. All right. So then we are just going to continue. So here's our read GOT entry. We have called our using it function, as you can see. Wow, I didn't know I could drag windows with my mouse. And then let's see, we are currently broken, waiting for input. So we'll type context to get our, oh, come on, yeah, there we go. All right, we're in the read call. And so we can see that we've called vuln, we've called use it. And I probably should have put some breakpoints down earlier. So that's what I'm going to do. Not everyone's perfect. So let's go into vuln again. I'm very running out of time, so we're going to get there, I swear. And I'm interested in what happens right after that read call happens. So break star read at 62 or vuln. So we'll continue once. This is our first read call. So that's the one that's getting us our leaks. And then the next read call is the one that's actually sending in our payload, this guy right here. So if we step one instruction forward, we've stepped over the read call and finished. And now I should be able to see that GOT address show up on the stack. And if we look, here's all of our A's. Here's that 8 null bytes that we wrote. And then here's the GOT entry for put char. So like this is the literal address of that. We can confirm this just by taking a look at it. And so now when we pass it into that next function, we're going to be allowed to just write 8 bytes there. So if I continue, we'll notice that now we're in use it. We're broken on read. We have a buffer that's literally pointing to the put char GOT entry and lets us write 8 bytes over it. We're essentially done now. At this point, I would pretty much just slam the address of read there and continue. Or sorry, the address of a win function, which, by the way, because we have this elf object, I can do elf.functions win.address. So P64. I do have a win function. You didn't see it, but it is there. And then I will also just do a receive until that one string of using it. Just because what can happen if you're not careful is your input will get stacked up together. And sometimes you can have 2 read calls that in Python jam together and then get consumed by the same read call over on your binary. So make sure that you're managing the states of your program correctly, or else you can run into funny situations where because if I didn't have this, Pwn.tools will run both of these back to back. The input will all go into the tube, and then the read hex 100 will consume all of it. So that's why I have this receive until there. And then in theory, we should have a P interacted. Let's see if this works one shot, but otherwise, in the interest of time, boom, boom, boom. And boom, there's my local flag. We have overwritten put char with win and jumped there. So before I round out, is there any final questions on kind of what this is looking like? Hopefully this clears up a little bit of kind of how you can use these tools together. Big takeaways. Don't get stuck on stupid things. Ask questions in the Discord. Like if you're running into something that you feel is stupid, like we've all been there. I spent an hour debugging this demo because I forgot to disable Railroad. And so it's like, why can't I write to the GOT? I'm going crazy. So it's like, these are the kind of things where it's like the sanity checks that the Discord has are very, very helpful. Use it.
What's the difference between full and partial railroad? Like this one is no railroad, and the other one are partial.
Yes. So I don't know the 100% the specifics off the top of my head. My understanding is that full railroad will resolve the entire GOT before the binary starts and then make the whole thing non-writable. And then partial, I believe, does like a subset of it.
So the GOT itself contains more than just function pointers. What we're talking about, we say the GOT
Yeah.
is a subset of the GOT. The GOT resolves all sorts of global symbols, not just functions. But what's interesting to us in the context of exploitation are function pointers. So that allows us to gain control of them. Yeah. The GOT.
All right.
Subsection of the GOT.
Bang. Wow, that camera's really zoomed in. That's